if you have a Markov chain, xn, which is aperiodic and irreducible, if we call mu n the distribution at time n, so this is the probability that xn is equal to x, then we want to prove that mu n converge to pi, where pi is the unique stationary state of this Markov chain, right? So this is what we want to prove. And as I said, I will present a coupling argument. But before, well, the coupling argument will use some properties. So let me first talk about the strong Markov property. So remember, we defined stopping time as a function with the property that t equal to n belongs to Fn, which is the sigma algebra generated by x0, x1, xn for all n. And we have seen that the heating time is stopping time. Another example is the return time. Which I will represent by H. So if I have a subset A of E, H of A will be the minimum of all n larger than 1, such that xn belongs to A. So mind that for the stopping time, this minimum was taken from n larger or equal than 0. So if you start from A, your heating time is just 0. Now you're taking a minimum for n larger or equal to 1, so it's really the return time. Okay? So even if you start from A, well, you wait until you return to A. Okay? And it's clear that H of A, it's a stopping time. So to prove that H of A, it's a stopping time, you need to show that this set belongs to Fk, and, well, H of A is equal to K if and only if x1 does not belong to A till xk minus 1 does not belong to A, and xk belongs to A. And this is for k larger or equal to 1. And for k equal to 0, HA equal to 0 is just the empty set, which of course belongs to F0, while these ones belong to Fk. Okay? So it's another example of stopping time. And of course, you can define the third time you visit a set. That will be a stopping time. So these are examples. So now I will define a sigma field, which is extremely important. So in some sense, I can understand Fn as the information available at time n. Right? Because, well, it's the sigma field generated by x0, xn. At time n, what you know is what happened to your process until that time, which means all positions until that time. So I will understood this sigma algebra, this sigma field, as the information available at time n. Now, if I give you a stopping time, so let's say the first time you hit the set A, then you have also an information which is the information available up to this random time t, the information available up to the stopping time. But how would you formalize this set? So everything which is known at time t. So here is the definition. I will say, so I fix t as stopping time. And I define as ft as the set of all a in F. So remember, we are working in a big space, omega. So this Markov chain is defined in omega fp, and we know that all these variables xn are f measurable. Well, ft will be all the sets A in F such that A intersection t equal to n belongs to Fn for all n larger or equal than 0. Right? Which means that if the stopping time is equal to n, then A belongs to, if you take the intersection, then A belongs to Fn. And well, I leave it to you to check a simple exercise that Ft is indeed a sigma algebra. Okay, that's very easy. So this sigma algebra will be very important when studying Markov chains, because what we have seen is that, well, if I know all the story of the process until time n, and I know that at time n I am at some position x, then what happens after this time? Well, it's a new Markov chain which starts from x. Well, we will extend this property to stopping times. So if I know what happened until a stopping time t, and if I observe now the process starting at this time t, then what I observe, it's a new Markov chain which starts from the position at time t. Okay? And this is the strong Markov property. So we are extending the Markov property to times which are random, to stopping times. So what I want to, the theorem which I want to prove is the following. Consider the probability of fix a stopping time t, and fix an event which happens after this time. So let's say xt plus 1, it's equal to x1, xt plus k, it's equal to xk, and take this probability conditioned to all information available up to time t, which we have seen it's ft. So this is a conditional probability, okay, or a conditional expectation. And what I claim is that this conditional probability, it's equal to p xt, x1 equal to x1, xk equal to xk. And this in the set that t is finite. Okay, so I'm saying that some conditional expectation, it's given by an expression, but the way in which I understand this identity is that, well, if I know everything up to time t, and if I'm interested in an event which happens in the future, then this conditional probability, it's actually observing a new Markov chain which starts at time 0 from xt and observing it starting from that time. All right? And so, of course, well, this happens for all k, for all x1, xk. And, okay. So is the statement clear?
What do you mean exactly by t less than infinity?
Sorry?
About t less than infinity, how do you introduce this in the identity?
So I'm saying that these two events are equal on this set. Because,
with this set.
yeah, because if t is equal to plus infinity, well, this object here has no meaning. So I'm really taking, this is an ft measurable object. So it's a function which is ft measurable. I have here another function which is measurable. I'll show that it's ft measurable. And I'm saying that these two functions on this set, they are equal. Okay, so before I prove that, let me prove the same statement, but replacing the stopping time by a fixed time. So what I want to show you is that while the same identity holds if I replace t by a fixed time. So what I'm saying is that if you take xn plus 1 equal to x1, xn plus k equal to xk, given fn, then what I'm saying is that this is equal to the probability starting from xn, that x1 is equal to x1, xk is equal to xk. Okay. So let's prove this statement. Okay? So I have here a conditional probability or conditional expectation, and I want to prove that this conditional expectation is equal to that expression. We have seen that in order to do that, you have to prove two. So let me call that, a function g. If I want to show that this conditional probability or expectation is equal to g, I have to prove two things. First, that g is fn measurable. And second, that for all a in fn, the expectation of a with respect to the first it's equal to the second. All right? In order to prove that this function is indeed equal to that conditional expectation, I have to prove these two properties. So let's do that. So first, it's clear because it's a function of xn, right? This probability, this expression, it's a function of xn. And xn, it's fn measurable. Okay, so p of xn, it's actually a function of xn, and xn it's measurable, so this is indeed fn measurable. Okay? So it remains to prove the second property, and to prove the second property, well, in order to prove, I think a in fn, so all elements a in fn can be written as a union of a set which is like x0 equal to y0, xn equal to yn. Okay? If I take, since A is the sigma algebra generated by x0, xn, then I can write any element of fn as a finite union of these sets because E is a finite set. So it's enough to take A of this form, and by taking A of this form, what I need to show is that the expectation of the indicator, so well, I didn't say, but chi is the indicator, right? Chi is a function which is equal to 1 on the set A and 0 otherwise. So chi of x0 equal to y0 up to xn equal to yn of the probability that xn plus 1 is equal to x1, xn plus k is equal to xn plus k given fn. Okay, so this is the left-hand side. So, well, this object here, it's Fn measurable. So the expectation of this, it's equal to the probability that x0 is equal to y0, xn equal to yn, xn plus 1 equal to x1, xn plus k equal to xn plus k. Right? Because, well, this set, it's Fn measurable, so I can put it here inside. And then I can use the fact that the expectation of the conditional expectation is equal to the expectation to get that this is equal to that. And once I do that, let's use the property we proved already, that conditional to the present, past and future are independent. So what we do, I condition that on xn it's equal to yn. So this is equal to the same event. So here it's x0 equal to y0 up to xn plus k it's equal to xn plus k. Given that xn is equal to yn times the probability that xn is equal to yn. Now, let's use that past and future are conditionally independent to rewrite this expression as the probability that x0 is equal to y0 till xn is equal to yn, given that xn is equal to yn, times the probability that xn plus 1 is equal to x1, xn plus k is equal to xk, given that xn is equal to yn, times the probability that xn is equal to yn. So here I'm using a property I already proved, that past and future are conditionally independent. Okay. Now I can use the fact that given the present, then the future is just a new Markov chain starting from the position. So this will allow me to rewrite the second term. And for the first term, well, I'll just rewrite the first term as the probability that x0, so I have a conditional probability times this probability, this becomes the probability of the intersection, which is x0 equal to y0, xn equal to yn. So this is the first term, so these two. And then I have this last one, which I use the Markov property to say that this is x1 equal to x1, xn xk equal to xk. So what we proved is that this expectation is equal to that one. So now to have exactly the same formula, let me write this expectation as this probability as the expectation of the indicator function. And well, this is a constant, so let me put it inside the expectation. And finally, well, since xn is equal to yn, and I have here yn, okay, I can replace yn by xn to get exactly what's written here. So since in this set xn is equal to yn, I can replace this yn by xn. And if you observe, since this is exactly what's the identity I wanted to prove. So questions about this proof? Okay, so it's another way in which you can write the Markov property, saying that, well, actually, this identity holds. Okay, so essentially, we proved the strong Markov property for stopping times which are constant. Now let's extend this result to stopping times. So questions? Okay. So maybe let me So again, I want to prove this identity, I need to show these two properties. So the first one is that the right-hand side is ft measurable, and then that for all a in ft that we have these relations. So to prove the first one, I have to show that xt is ft measurable. Okay, to prove that, I have to show that, well, xt, if I take the inverse image of xt of a set A, then this belongs to ft. Okay, xt, it's a function from omega to e. To prove that this is ft measurable, I have to take an inverse image and to show that it belongs to ft. To prove that a set belongs to ft, I have to take the intersection of this set with t equal to n and prove that it's in fn. So I fix n larger than 0, and I consider xt inverse A. So A is a subset of E. Right, xt takes value in E, so I take an inverse image. And by definition, to show that it belongs to ft, I have to show that for any n, this set belongs to t equal to n. Okay, but what is this set? This set, it's the set of omegas in omega such that xt of omega belongs to A. Okay, mind that xt, just what is the function ft? When you compute it at omega, this is where you compute t of omega. So t of omega is an integer, and so this gives you an integer, and you compute. Okay, so this is the definition of this function. So now I'm taking here all the omegas for which xt of omega belongs to A. But I know that t is equal to n. So this set coincides with the set omega in omega such that xn, so I will replace t of omega by n. Xn of omega belongs to A, intersection t equal to n. But t is a stopping time, so t equal to n belongs to fn. Xn, of course, belongs to fn. Therefore, the intersection belongs to fn, and which proves that, indeed, this set is in fn, and therefore, that xt is ft measurable. And since the right-hand side, it's a function of xt, this object is ft measurable. So this is the first property we have to prove. Now let's prove the second one. So let me take, so I have to prove that in this set, these two objects are equal. So let's take A in ft. Maybe A it's not. Lambda in ft. And I need to prove that the expectation of the indicator of lambda. So I have to prove that these two objects are equal on the set t is less than infinity, so intersection t less than infinity. Then the probability that xt plus 1 is equal to 1, xt plus k is equal to xk given ft. Okay, that this is equal to that. Okay, I get the same expression, but in which I can replace the left-hand side by the right-hand side. Okay, so I want to finish with the same expression, but instead of this conditional probability, I'll have this one. On the set t less than infinity. Fine. But since t is less than infinity, I can replace this set by t equal to k and make an union over k. And since they are disjoint, this is equal to the sum for n larger or equal than 0, that the expectation chi lambda intersection t equal to k, and this probability, this conditional probability. N, yes. Thanks. And this conditional probability. Okay. Well, A belongs to lambda belongs to ft. Tau equal to n belongs to ft. I guess that's clear because I've taken that intersection t equal to k. It's either empty or t equal to n. So it always belongs to fk. So again, since these are measurable, I can put them inside and just erase the conditional expectation. So, okay, so maybe let me do it step by step. So first, this object is ft. so it can go inside of the conditional expectation. Okay? And so this is equal to the expectation of the conditional expectation of chi lambda intersection t equal to n intersection x t plus 1 equal to x1, x t plus k equal to xk, given ft. Okay. I will write this probability as an expectation of the indicator function, and then I introduce this object because it's ft measurable. Now, since t equal to n, I can replace here t by n and here by, well, first I'll just say that the expectation of a conditional expectation is equal to the expectation. So now we don't have conditional expectation anymore, just the expectation. Now, since t is equal to n, I can replace here t by n. Okay, I don't want to erase anything. So what I will do now is I will take the conditional expectation with respect to Fn. So I have here an expectation. This set lambda intersection t equal to n belongs to Fn, because lambda belongs to Ft. Okay. So if I have this expectation and I take the conditional expectation inside with respect to Fn, this indicator will get out from the conditional expectation. And this is equal to the indicator of lambda intersection t equal to n. And then I have the conditional expectation of xn plus 1 up to xn plus k given Fn. Right? I did exactly these steps in the other way. I first compute the expectation of the conditional expectation. Then I realized that this is Fn measurable, so I took it out from the conditional expectation. And now I can apply. Okay, so I reached that point. And at that point, I look at the Markov property. And what I see at the Markov property is this is exactly what we have. So I can replace the conditional expectation of the conditional probability by this probability. So by what we proved, this is equal to n larger than 0 of the expectation of the probability. Now we are starting from xn, and we have that x1 is equal to x1, xk is equal to xk. All right? This is by the Markov property we proved. Now, since t is equal to n, I can replace xn by xt. And once I replace n by t, I can sum over n to get that this is equal to the expectation of chi lambda intersection t, it's finite, of the probability of what's written here. And this proves, therefore, that these two expressions are equal on the set t infinity. So I'm taking the intersection here on both sides, and I'm taking the expectation. Okay? So that proves the strong Markov property, which is saying, well, if you have a stopping time, whenever you are at this stopping time, what you observe, it's a new, so you lose memory. Everything which happened before is not important to compute the probabilities of the future, just the position at which you are at that time. Okay, questions? So before we proceed, let me give you an application of that. So we still have E finite and P irreducible aperiodic. Okay. These will be my assumptions from all time. And what I claim is the following: either, so you fix a point, x, you start from x, and you ask yourself, well, what is the probability that xn visits x infinitely often? Okay, so you are at x, and you ask yourself, well, what is the probability that I will return to x infinitely often? Okay, let's remove the assumption of irreducibility. And what I claim is that this is either 0 or 1. So that this is an event which has either probability 0 or probability 1. So in the irreducible case, it's always equal to 1. And this is a consequence of the strong Markov property. Because if you are at x, well, either you have a positive probability of never returning to x. So there is a probability that you'll never return to x. So in this example, for instance, so a very simple example, you jump from one point to the same point with probability 1/3, say, and here you remain. Okay, so starting from this point, there is a positive probability that you'll never return to this point, okay, in this case. Here an example which is not irreducible. Okay? So what I claim is that if there is this positive probability, now let's observe the return times to x. So you start from x, and maybe you do a very long excursion, but then you return to x. Okay? So at that time, you start your process again. So each time you visit x, you're starting your process again. And each time you visit x, well, there is a positive probability that you'll never return to x. So the number of returns to x will be a geometric, right? Because, well, you are at x, there is a positive probability you never return, but if you return, you start again. So at this point, there is a positive probability you never return, or you return. So the number of times you will return will have a geometric distribution. Therefore, we'll have a finite expectation, and the number of times will be finite with probability 1. The number of times you visit X. Questions? So this is the idea. So let's turn this idea into a proof. So what I'm saying is that, well, there are two possibilities. Either starting from X, remember that h of X is the return time to X, and this is a stopping time. So the probability that this is finite, it's either 1 or it's smaller than 1. And what I claim is that if it's 1, this means that you return. So the probability that starting from X, you visit X infinitely often, this is 1. And if it's less than 1, then this probability is 0. Okay, so I'll prove the first one and leave it to you as an exercise, the second one. Okay, so you see that you have a dichotomy, right? And let's say that if this probability is 1, you call this site recurrent, so that you visit it infinitely many times. Otherwise, you call it transient, because, well, at some point you stop visiting this site, this point. So let's assume that the probability is 1. And let's prove that you visit infinitely often. So let me call maybe n the number of visits to X. And what you want to prove is that n is equal to plus infinity. So that this probability is equal to 1. So to prove that, what we'll show is that the probability that it's larger than k, it's equal to 1 for all k. So let's prove that by induction. The probability that you visit at least one time, this is the probability that you return. And this, by assumption, it's equal to 1. Now, just to avoid writing hx, let me call tau this return time. And let's assume that we proved that n is larger than k with probability 1. So we proved that for k equal to 1. So now let's prove it for k plus 1. And let me call y the chain, which is the chain starting from the first visit to the return time to X. So y at n, it's X tau plus n. So it's just a chain I know that n is larger than k with probability 1, so it's larger than 1. So this time it's finite. The return time is finite. And so this is well defined. This chain is well defined. It's the chain starting from tau. And what we are proving here is that given ft, so this is a new Markov chain which starts from x. Okay, so if you put yourself at time t, tau, what you see, yn, which is this chain, it's a new Markov chain which starts from x. Okay, so I want to prove that n it's larger than k plus 1 with probability 1. My assumption is that hx is finite, so tau is finite. So this is the same thing if I put tau finite and n larger or equal than k plus 1. Okay. So here, so this event is the event that the chain x visits at least k plus 1 times site x. Well, this is the same thing as that the chain y visits x at least k time. Okay? So to say that the original chain visits x at least k plus 1 time, it's the same thing as asking, given that you return it once, that the chain y is visiting x k times. Now I can rewrite this probability as the expectation of the conditional expectation that of this event, so that, or the probability, conditional probability that tau is finite and n of y is larger or equal than k, given f tau. But the event that tau is finite, it's ft measurable. Okay. To show that tau is this set, it's ft measurable, you intersect it with tau equal to n, and it has to belong to fn. So since it's ft measurable, I can remove it from the probability. But now I've seen that on the set at which tau is finite, this conditional expectation is just the conditional expectation starting from x tau of the process starting at x tau times 0. So that this, by the strong Markov property, this is equal to the probability starting from x tau of n. Now, this chain was the chain starting from tau, but once you take the conditional expectation with respect to f tau, it becomes the original chain, that eta x is larger or equal to k. Right? So this is a tricky step, but this is exactly what we proved. Okay? we looked at the chain starting from tau, and this chain I'm calling it y. And what we proved is that given f tau, this chain, the conditional expectation, it's exactly equal to the probability starting from x tau of the original chain starting at time 0. Okay, so this is the strong Markov property. But tau, it's the return time to x. So the position at time tau of the process, it's x. So on the set in which tau is finite, this is x. Okay, because tau is the return time, which means that at time tau, I'm at x. So once I replace x tau by x, this becomes a number. It gets out from the expectation, and it remains the probability that I'm starting from x, that tau is finite. So what we proved that the probability that starting from x, that n is larger or equal than k plus 1, it's equal to the probability that starting from x, n x is larger than k times this factor. And this is what I was telling you, that a geometric distribution appears. Okay, because if this was less than 1, you'll just get that these probabilities decay exponentially with this factor. And so, well, in our case, this is 1. So we get that the probability that n is larger than k plus 1 is equal to the probability that n is larger than k. And we already proved that the probability that n is larger than 1 is 1. And this proves that for all k, this probability is 1. So we can send k to infinity to get that probability that n is equal to infinity, it's 1. Okay? So we just proved this fact, that if this probability is 1, then you visit x infinitely often. While the same argument will show that if it's less than 1, then you visit it. The distribution of the number of visits, it's given by a geometric distribution. Okay, and therefore has finite expectation, which means that well, the number of visits is not only finite, but has also finite expectation. Questions? So I recommend you exercise in order just to get familiar with these property, or how to use this property. Okay. Maybe I'll select some exercise to propose. Fine. So this was about the strong Markov property, which is essential in this theory. Now I want to go back to coupling and the proof of the theorem which I announced. So I have a Markov chain, which means that I have some transition matrix P. And I have a Markov chain, Xn. Now I will say that a pair Xn, Yn, so this is now a process, but which takes value in E times E. Okay? I will say that this is a coupling So this is a Markov chain on this space. So it takes value now on E times E. And I would say that this Markov chain, which takes value on E times E, is a coupling of the Markov chain, my original Markov chain, maybe let's use another name, Zn. It's a coupling of Zn. If the following property holds, that if I just look at the first coordinate, what I observe, it's a Markov chain with transition matrix P. And if I look at the second coordinate, I observe the same thing. Okay? So this means that, let me call Q the transition matrix of this new Markov chain. So now Q is defined on the product space. So I'm jumping from a pair xy to a new pair x prime y prime with some probability. So I'll say that this is a coupling. Okay, there are two ways I can define that. One which is an algebraic way. So let's say that for all y and x, the sum over y prime of q x y q x prime y prime. So I'm summing over all. So I'm starting from a point. I'm summing over all second coordinates, and I want that to be equal to p x x prime. So it can't depend on y. Okay? It can't depend on y. So in principle, this object depends on y, but I don't want it to depend on y. So whatever the value of the second coordinate, if I look at the first coordinate, what I observe, it's a jump with the probabilities given by the original transition matrix. And the same thing for the other coordinate. So for all xy, q, x, y, x prime, y prime, that will be equal to p, y, y prime. Okay, and an example is just take two independent copies of your Markov chain. Okay, if you take q, xy, x prime, y prime equal to px x prime, py y prime, you see that if I sum over y prime, this expression, this is summing this expression over y prime, and this is 1. So I get px x prime. And the same thing if I sum over all x prime. Fine? So this is what I will call a coupling. And the idea is this one, so that if you just observe the first coordinate, what you observe, the dynamics you observe, it's the original dynamics. And the same thing for the second coordinate. Now I want to prove two lemmas. So the first one tells me that if I have a chain xn, which is aperiodic and irreducible, then the probability that starting from x I visit y in finite time, so this is 1 for all x, y. So this is the return time, and saying that if you are periodic and irreducible, starting from any point, eventually you'll visit a point. And what is the idea? Well, the idea is the following. I told you that if the chain is irreducible and aperiodic, then for all xy, there exists n0, for all, what I said is the following: for all xy, there exists an integer which depends on x and y, such that the probability that you jump from x to y is positive for all n larger than n xy. Okay, so do you remember we discussed this last class? First we proved that for x to x, and then y to x. And this was using a result in number theory. Okay, but since our space is finite, I just take the maximum of these nxy, and what I get is that there exists n0 such that for all xy, Pn xy, it's positive if n is larger than n0. Okay? Since there are only a finite number of pairs, I can get a uniform n0. So I have this n0, and what I will do is I will observe my process at these times. And I know that starting from x, so there is a point y, which I want to visit. Okay, and I start from, yes? X prime, sorry, which definition? The first sum, it's over y prime. No. What I'm saying is that you fix, okay, you want x prime here, you're right. Is that your question?
Yeah, I was asking if it was fixed or that sum should also be in x prime.
No. So what I'm saying is that for all y x prime, you have this identity. So this is really telling you whatever y, so you have these, your space E times E, and you look at x, whatever y, the probability to jump from this position to this position should not depend on y. So you really, if you look just at the first coordinate, so you look x and x prime, so the probability that you'll jump from this point, okay, this point to this point, in principle, it should depend on which y you are, but I don't want it to depend. So if I sum here, in this line, this is what I'm doing here, this sum do not depend on this point, this line. And the same thing for. Okay, and here, so here there is also a y prime. Okay? Other questions? Okay. So back here, so we know that there is this n0. And also that I can jump from any point here to any point here. And what I will do is I will then look at my process at these times, n0, 2, n0, 3, n0, and so on. And what I'm saying is that is the following. So I'm starting from x. So there is a positive probability that I jumped to x, that I'm at y at this time n0. Okay. If I'm at y, I'm fine, but maybe I'm not at y, I'm at some other point. So what is the probability that I will never visit y? The probability that I will never visit y, starting from x, is that, well, I don't visit in my first jump. But when I first jumped, my process is starting again. And if I don't want to visit x, y, never, I have also, I'm forbidden to visit y in my second step. And I'm forbidden to visit y in my third step, and so on. But the probability that I visit y, it's positive for all points. So if I take the minimum, there is a positive probability that I visit y. So the probability that I visit anybody else, it's bounded above by a constant which is strictly less than 1. And since I have to repeat that infinitely many times, the probability is 0. Okay, so maybe I repeat. So I found this n0 for which this probability is strictly positive for all x and y. Okay. Now I want to compute what is the probability that I will never visit y. Well, if I never visit y, this means that in this first step, I'm not allowed to visit y. In the second step, I'm not allowed to visit y. In the third step, I'm not allowed to visit y, and so on. But these are independent, given the position. So since all these probabilities are positive, this means the probability that I do not visit y is bounded by a constant which is less than 1. And therefore, the maximum, it's also bounded by a constant which is less than 1. So the probability that I do not visit y in my first jump, it's bounded by something less than 1. Then, wherever I started, I arrived here, there is again a positive probability bounded by a constant less than 1 that I will not reach y at time 2 and 0, and so on. So not visiting y by using the Markov property, not visiting y 3 times, will be bounded by this constant to the power 3. And since this constant is smaller than 1, taking these 3 to infinity will get me 0. Okay, so let's write it down. You look not convinced. So I want to show that what I'm proving is actually that the probability that hy is equal to infinity is 0. Okay? So this is where my argument is leading me. And so let's go back to this fact. Do you agree that there exists this n0 for which this probability is really positive? Do you agree with that? Okay. So if this it's really positive, then Okay, let me call this y0. So I fixed y0. And now what I'm saying is that the minimum, so let me call A, the minimum in X, in E, of P and 0, xy, 0. Okay? Since these probabilities are all positive and the set A it's finite, this A it's really positive. Okay? Which means that P, okay, which means that 1 minus P n x which is the probability so these probabilities are all bounded below by this A. So this object here, it's less or equal than 1 minus A. So this is bounded by 1 minus A. Okay? Because these P's n are all larger than A, which is the minimum. So they are all larger than A, which means that 1 minus A is less than 1 minus A. 1 minus P is less than 1 minus A, so and this is this probability. Okay. So I know that. You agree with this? So this probability that you never visit y0. Questions, or you agree? If I'm messy, just tell me and try to make it clear. Okay, so what I'm saying is that this probability that you never visit y0, it's less or equal than the probability that you do not visit y0 at time n0. You do not visit y0 at time 2n0, and you do not visit y0 at time kn0. Fine? But this is equal, so let's use the Markov property, say now at time k minus 1 and 0. So we are in the penultimate time. And let's write this as the expectation starting from x of the conditional expectation that x, or the conditional probability, that xn0 is different from y0, xkn0 is different from y0, given f k minus 1 and 0. So I'm fixing at the penultimate event. Now, at this time, I know x0, I know xn0, I know xk and k minus 1 and 0. All these are measurable with respect to that. So I can write that this is equal to the expectations starting from x, that x n0 is different from y, x k minus 1 n0 is different from y, and the probability that x, k, and 0 is different from y, given f, k minus 1, and 0. Because they are all measurable. Okay? Well, fine. But now let's use the Markov property to say that this is equal. So I know everything up to time k minus 1 and 0, and I'm computing an event at time k and 0. So by the Markov property, this is the probability that I'm starting from k minus 1 and 0, and I want to be at time n 0 in a point different from y. So this is the Markov property. Okay? Given everything which happened up to a time, given this, well, what I observe in the future, it's a new Markov chain which is starting from the position at this time. All right? But xk minus 1 and 0 is different from y. So this position here is different from y. So the probability that starting from this position, I'm not at y at time 0, is this, which is bounded by 1 minus a. Because this estimate is uniform over all positions. So this probability here, it's bounded by 1 minus a. And this is a constant. It gets out from the expectation, and what remains that this is bounded by 1 minus a, the probability starting from x, that x and 0 is different from y, x k minus 1 and 0 is different from y. And I can repeat this argument to show that this is bounded by 1 minus a to the power k. Okay, so what I proved is that this probability is bounded by 1 minus a to the power k for all k. A it's positive. So as k tends to infinity, this goes to 0. And this is what I wanted to prove. Fine? So we just proved that in the aperiodic irreducible case, starting from any point, you visit any point in finite time. Questions? So my second lemma it's take this xn, which is aperiodic and irreducible, and define this coupling. So I defined a new Markov chain which has transition matrix Q, which is xy, which jumps from xy to x prime y prime with probability px x prime, py y prime. And we have seen that this is a coupling of the Markov chain. Okay? Now what I claim is that the coupling, it's also aperiodic. It's also aperiodic and irreducible. Okay. Well, why is that so? I will use the same argument. I know that there exists n0 for which Pn xy it's positive for all n larger than n0. So this will extend to Q by definition. So I know that P is aperiodic and irreducible. From that, I deduce that there exists this n0 for which Pnxy is strictly positive for all n larger than 0. Now I claim that Q n xy x prime y prime, it's strictly positive for all n larger than n0, x, y, x prime, y prime. Okay, and this is obvious because, well, this probability will be equal to Pn x x prime, Pn y y prime. Okay, so this is equal. So if you just compute the product of Q with Q, what you'll get is will be P and P. So what I claim is that this is equal to Pn x x prime, Pn y y prime. Okay, just take n equal to 2 to convince yourself that you're multiplying this matrix with itself. Since this matrix is written like that, actually you will be multiplying P with P and Q and P with P to get this formula. And since you know that this is strictly positive, this is strictly positive for Q. Okay? So we know that. So this tells you that it's aperiodic because, well, you start from n0, Q. If you take xy, xy, you know that Qn xy, xy, it's strictly positive for all n larger than n0, so the greatest common divisor has to be 1, okay, because the set contains all integers starting from 1 and from n0, from one integer. So it's aperiodic, and it's also irreducible. It's irreducible because it's positive. Okay, so the coupling, it's aperiodic and irreducible. Questions? So now we are in a position to prove the theorem. So let me remind the theorem. So we take a measure mu, which is a probability measure on E. You define mu n as the distribution at time n for the Markov chain which starts from mu, and you want to show that this converges to pi. And here, again, I'm assuming that E is finite and that the chain is aperiodic and irreducible. So what I will do, I'll define a coupling. So this is time, and this is the space E, and this is time 0. So x0 will be distributed according to pi. So I want the probability of x0 to be equal to x, this to be pi of x. And I want the probability of y0 to be y. So the initial distribution of y will be mu. Okay. So I start x from pi, the stationary distribution, and I start y from mu, which is the probability measure given in the hypothesis of the lemma. And now I let the couple xn, yn evolve according to this coupling. Okay? So I have a new Markov chain which jumps from xy to x prime y according to these probabilities. So they jump. So let's say that x0 started from this point, y0 started from that point, and they started jumping. So this is time 1. what I claim is that at some point they will meet. They will meet on one point. Okay? I'll prove that they will meet in finite time, and they will meet, let's say I'll fix here a point z, and I want them to meet at z. So I look at the first time the pair xy, it's equal to z, and I will show that this the probability that this happens in finite time is 1. And then they continue. So maybe this is y, and this is x. Okay. Now I'll define a new process, which is z. And what z does is that z follows y up to the heating time. So let's say that here is y and here is x. So z will follow y until the first time they hit at zz. And at this point, instead of following y, z will follow x. So I'm defining a new process, Zn, which is equal to follows y until this heating time, and then follows x. So let me define Z. So to define z, I first have to define the heating time. So let me fix z in E, or maybe W. And let's define tau as the heating time of the point WW for decoupling. So this is the minimum for all n larger than 0, such that xn, yn, it's equal to WW. Okay, the heating time of this point. I know from the fact that this coupling, it's aperiodic and irreducible, that this time it's finite. Okay? We prove that if we have a chain which is aperiodic and irreducible, then every point is visited with probability 1 in finite time. So I know that for the chain Q, tau, it's finite with probability 1. Okay? Now, since, well, on the set in which tau is finite, which is a set of probability 1, I will define a new process, Zn. And as I said, Zn will follow Yn until the heating time, and then will follow x. So Zn will be Yn for n between 0 and this heating time tau, and then xn for n larger than tau. So I'm defining a new process. Okay? Clear the definition? So my claim first, an obvious one is that the initial distribution of Z, it's given by mu. So Q that z0 is equal to x, this is mu of x. Because at time 0, z is equal to y. And as I said, this Markov chain, the pair will be starting from, the second coordinate will start from mu. Okay, so I want that the probability that x0 is equal to x and y0 is equal to y. So this means the initial distribution of the pair, I will define that by pi x mu y. Okay, so this is a probability on E times E. And if I look at the second coordinate, the distribution of the second coordinate is mu, the distribution of the first coordinate is pi. So x0 is distributed according to pi, and y according to mu, y0 according to mu. Okay? So since z at time 0 is equal to y at time 0, this distribution is equal to mu. Fine? So this is easy, but now my claim, the important part of the claim, is that Zn, it's a Markov chain. I claim that Zn is a Markov chain. And in order to prove that, I have to compute, say, what is the probability that Zn plus 1 is equal to Zn plus 1, given that Z0 is equal to Z0 till Zn is equal to Zn. And what I want to show is that this is P Zn plus 1. Okay? This is what one way to show that Cn has is a Markov chain with transition matrix P. So let's compute this probability, and by computing this probability, what we'll do is we'll take the intersection and I'll divide by the numerator. Okay? So I have to compute the probability that Zn plus 1 is equal to Zn, Z0 is equal to 0, Zn equal to Z, Zn divided by the probability of this event. Okay? This is by definition of conditional probability. And so let's compute the numerator. Well, I have to know the value of tau, okay? Because the definition of Zn depends on tau, so let's divide that according to the value of tau. So let's do a sum for k larger than 0 of the probability of the same expression given that tau is equal to k. Now, this is a sum over k. So the probability I'm computing is the probability of all these events. Now, tau is equal to k. Well, either k is larger or equal than n, or k is smaller than n. Okay? So I'll sum k going from 0 to n minus 1. If tau takes the value k, this means that z0 up to zk is equal to y, and then it's equal to x. So this probability is the probability that y0 is equal to y0 up to yk it's equal to yk, z0, I'm sorry. And then, starting from time k plus 1, this is x. and I'm going up to n. Okay, n plus the probability and if k is larger or equal than n, this is just z is equal to y. Okay? Yeah, you're right. Thanks. And therefore, this is up to n, and this is n plus 1. Okay, thank you. Fine. Now, let's take conditional expectation with respect to fk in this probability. Okay? So I'll take in this first probability say that the probability is equal to the expectation of the conditional probability given fk. And when I take given fk, all these, and fk now, mind, it's the sigma algebra generated by xj, yj, for j between 0 and k. Okay? So when I take the conditional expectation with respect to fk, all these objects here, all these variables, are fk measurable. So this is equal to the sum of the expectation of tau, it's equal to k, y0, it's equal to y0, z0, yk, it's equal to zk, and then the conditional probability of xk plus 1 up to xk n minus 1 given fk. But that I know that this is like you start a new chain, the new pair xy at time 0 from the position, and this is q, from the position xk, yk, and therefore this is the x1 equal to zk plus 1 up to x n minus k plus 1 equal to z n plus 1. Where here I'm using the Markov property. Na segunda soma você tem n mais 1 também. Exatamente. All right? So for the first sum, I first took the conditional expectation given fk. So all these terms are fk measurable. And then I have this, which depends on the future. So I know by the Markov property that this is like starting a new chain at the position xk, yk. and look at the event. Well, the event, it's x1 equal to zk plus 1 up to, well, here we have to rewrite n plus 1 as k plus n minus k plus 1. So at time n minus k plus 1 to be equal to zn plus 1. Okay? And I don't compute the second term, because this one I'll leave it as it is. Now, at this point, I know that tau is equal to k. But tau, it's the heating time of the point WW. So I know that xk, yk in the event tau equal to k are WW. And therefore, this probability gets out, this becomes a number, gets out from the expectation. And this, therefore, it's equal to Q W W, that x1, it's equal to z k plus 1, x n minus k plus 1, it's equal to z n plus 1. And now sum. Sorry, this is the sum, it's still here. And here I have the probability that y0 it's equal to z0, yk it's equal to zk, and tau it's equal to k. All right? Okay? Fine. Here's the trick. Now, this chain is starting at W. So this is actually equal to the probability starting from W that x1 is equal to zk plus 1, xnk plus, okay. But x and y have the same distribution. So I can rewrite this probability as y1 equal to zk plus 1 up to yn minus k plus 1 equal to zn plus 1. Actually, this is q. Okay, so I know that if I look at the first coordinate, what I observe, it's a Markov chain. So x moves like a Markov chain with transition probability p. So since this event only concerns x, this probability is the same thing as taking a Markov chain, which starts from W, and impose that at time 1, it's at zk plus 1, at time n minus k plus 1, it's at zn plus 1. Okay? Because this coupling, if I look at the first marginal, it evolves as the original Markov chain. But x evolves exactly as y. They have the same, the difference is in their initial distribution. But here I'm fixing the initial distribution to be y. So there is no difference between the evolution of x or y. So actually this probability is the same as that probability in which I replace x by y. All right? And when I do that, once I reach here, I can go backward in this computation and arrive at the end in which here, instead of x, I have y. So this is telling me that this probability is the same one in which instead of replacing if replacing z by y, because I replaced all the x by y's. So there are only y's now. Okay, so once I reach this point, well, if you don't agree, let me know. Once I reach this point, I can go backward in my computation. So, and wherever I have x, now I have y. Okay, so here it's not x anymore, it's y. And therefore, here I have only y's. And this is exactly equal to that, in which I only have y's. And therefore, the numerator, it's exactly this expression, but instead of having z's, I have y's. The same thing for the denominator, which tells me that indeed z is a Markov chain, because these probabilities are the same. Questions? Don't hesitate to ask questions if you don't understand, if it's not clear. Okay, so this proves that Z is a Markov chain. It's a Markov chain, and it starts from the distribution mu. Okay? Now it's the proof of the theorem, it's easy. So I don't erase that in case you have questions. So now I want to compare mu n of x with pi of x. Mu n of x, remember it's the probability that y at time n it's equal to x. But this is the same thing as the probability that Zn is equal to x. Right? Because Yn and mu n start from the same measure, and they are Markov chain with the same transition matrix. On the other hand, pi x, it's equal to the probability that xn is equal to x. Because x, it's starting from pi, and pi is the stationary distribution. Fine, but now let me compute this probability. Well, this probability, it's equal to Zn equal to x and tau, it's less than n, plus the probability that Zn it's equal to x and tau, let's say, smaller or equal, and tau it's larger than n. And this is true for any n. Okay. Now, if tau is less than n, at time tau, z change from y to x. So after time tau, so n, for n larger than tau, z is actually equal to x by our definition of z. So this probability is the probability that xn it's equal to x and tau it's less than n. Right? Because by definition of z, after time tau, z is equal to x. And this probability, I can rewrite it as the probability that xn it's equal to x minus the probability that xn it's equal to x and tau it's less than n. It's larger than n. and there is still this term here, which is the probability that z n, well, it's equal to x, and tau it's larger than n. So we wrote mu and x as these three expressions. Mind that this one is negative, this one is positive, and this means that if I take the absolute value between probability of Zn or Yn is equal to x minus the probability that Xn is equal to x, okay, so pi n is equal to x is the sum of these three expressions. So if I take pi, the probability that Yn is equal to x, minus this one, this difference, it's equal to these two expressions. Okay? One is positive, one is negative, so this difference in absolute value, it's bounded by the probability that tau it's larger than n. Okay? But we have seen that tau is finite, because tau is the hitting time of WW. So if I send n to infinity, this goes to 0, and this is pi x, and this is mu nx. So we just proved that mu nx is indeed converging to pi x, and we have a bound. Okay, actually, if you remember what we proved, you can show that this is exponentially small. So actually, you have exponential convergence. Okay, this is essentially, in my notation, 1 minus a n divided by n0. Okay. So this proves the theorem, not only the theorem, something a bit stronger, that you have exponential convergence to equilibrium. In the case of, here we used finite, irreducible, aperiodic. And all these assumptions are needed, as we have seen counterexamples. Okay? Well, I didn't discuss the infinite case, but in the finite case, you need a periodicity and you need irreducibility. Okay, so this is what I wanted to present today. So we'll continue tomorrow, if you have no questions.